Hello and welcome to ixamBee, where we help you to prepare 50% faster. I'm Dr. Sinishibu and this is mock test 3 of our IBPS SO IT Preliminary Exam Series. Over the next few minutes, we'll go through 25 carefully designed questions spanning computer networks, operating systems, cybersecurity, DBMS, data structures and algorithms, programming in Java and Python, OOPS concept, and computer organization. This set has a good mix of conceptual questions and numerical ones, so keep a notebook and a rough sheet ready. Every time a question comes up, pause the video, work it out yourself first, and then come back to check your approach against mine. This is how you'll actually build exam day speed and accuracy. So let us start. This is question 1. A network administrator is assigned the IP block 192.168.10.0/26. How many usable host addresses are available in this subnet and how many total subnets result when the standard /24 network is divided into /26 blocks? The correct answer here is option A, which is 62 usable hosts and 4 subnets. There are two things to calculate here, so let's take them one at a time. First is usable host. A /26 mask leaves 32 minus 26, which is 6 host bits. That gives us 2 to the power of 6, which is 64 total addresses, and we subtract 2 for the network address and the broadcast address, leaving 62 usable hosts. Second, the subnet count. We are going from the default /24 down to /26, which means we've borrowed 2 extra bits. 26 minus 24 equals 2. That gives us 2 to the power of 2, which is 4 subnets. Put both parts together, we get the answer, which is 62 usable hosts and 4 subnets, which is option A. Now let us look at question 2. During TCP connection establishment, which sequence correctly represents the three-way handshake between a client and a server? Here, the correct answer is option B. Walk through this the way it actually happens on the wire. The client always initiates sending a SYN segment to say, I'd like to open a connection. The server then responds with a single combined segment SYN and ACK. It's acknowledging the client's SYN while simultaneously proposing its own sequence number. Finally, the client sent back a plain ACK confirming the server's sequence number, and the connection is now fully established on both sides. So the correct order is option B. Let us look at question 3. The address resolution protocol, which resolves an IP address to a MAC address, functions at the boundary of which two OSI layers? The correct answer here is option C, which is data link and network layer. Look at exactly what ARP takes in and what it gives back. Its input is a network layer, layer 3 IP address, and its output is a data link layer, layer 2 MAC address. Since it's translating between an address type that belongs to layer 3 and an address type that belongs to layer 2, ARP sits right at the interface between those two layers. So the answer here is C, which is data link and network layer. In this question, which of the following port number protocol pairings is incorrect? So you have to identify the incorrect pair. So here the correct answer is option D, SSH with port number 23. This is the wrong pairing. This is a straightforward, well-known port recall question, but with a classic trap built in. SSH, which is secure shell, is actually assigned port 22, not port 23. Port 23 belongs to telnet. which is SSH's older unencrypted predecessor, and that mix-up is exactly what this question is testing. Every other pairing here is correct. So the answer here is that the incorrect pair is option D. Next we have which Linux command correctly sets a file's permissions so that the owner has read, write and execute access while the group and others each have only read access. Here the correct answer is option E, which is chmod 744 file name. Let's convert the required permissions into chmod's numeric notation, one group at a time. Each digit is the sum of read equals 4, write equals 2 and execute equals 1. The owner needs read, write and execute. That's 4 plus 2 plus 1, which is 7. The group needs read only. That's just 4. And others also need read only. Again, just 4. Put those three digits together in order: owner, group, others, and you will get 744. That's an exact match for what the question describes. So the answer here is E, chmod 744 file name. Now in question 6 we have which of the following algorithms uses a pair of mathematically related but distinct public and private keys for encryption and decryption. The correct answer here is option A, which is RSA. The phrase to focus on is a pair of mathematically related but distinct keys. That's the definition of asymmetric or public key cryptography, and RSA is the classic example of exactly that. A public key and a private key that are mathematically linked but different from each other. So the correct option here is option A. Next we have an attacker floods a target server with an overwhelming volume of traffic generated simultaneously from thousands of compromised devices across the internet, rendering the service unavailable to legitimate users. This describes which attack? The correct answer here is B, distributed denial of service or DDoS attack. The two key details here are thousands of compromised devices and overwhelming volume of traffic aimed at making a service unavailable. That combination, a distributed network of compromised machines, commonly called a botnet, flooding a target's bandwidth or resources simultaneously, is precisely what defines a DDoS attack. It's not SQL injection which targets a database through malicious input, and it's not phishing or man in the middle, which are about deception or interception rather than volume-based flooding. So the answer here is B, which is DDoS attack. In this next question, which property of a cryptographic hash function ensures it is computationally infeasible to find two different inputs that produce the identical output hash value? And the correct answer here is option C, which is collision resistance. Focus on exactly what's being described. Two different inputs producing the identical output. That specific scenario, two distinct inputs mapping to the same hash, is called a collision. And the property that makes such a collision computationally infeasible to find is called collision resistance. Don't confuse this with pre-image resistance, which is about not being able to reverse engineer the original input from a given hash output. That's a different, related but distinct property. So the property being described here is C, which is collision resistance. Next we have what is the 2's complement representation of the decimal number minus 25 using 8 bits. The correct answer here is option C, which is 11100011. Let's build this up step by step. First, write 25 in plain 8-bit binary. That's 00011001. Next, take the ones complement, which just means flipping every bit, which gives us 11100110. Finally, to get the 2's complement, we add 1 to that result, and the result would be 11100111. that final value, which is 1110011, is the correct 2's complement representation of negative 25. Hence, the answer here is C. Now, let us focus on this question. Consider employees with employee ID, name and department ID with department ID values 10, 20, 30 and null, and departments with department ID and department name containing only department ID 10 and 20. Which join applied as employees join departments will retain the employees with department ID is equal to 30 and department ID equal to null in the result, showing null for department name. The correct answer here is option E, which is left join. The key requirement here is that every row from employees must appear in the result, even the ones with no matching department. Department ID 30 and the null department ID with department name simply showing as null for those. That behavior, preserving every row from the left-hand table regardless of whether a match exists on the right, is exactly what a left join does. An inner join would drop those unmatched rows entirely, since inner joins only keep rows with a match on both the sides, and a right join would do the opposite of what we want. It would preserve unmatched department rows, not unmatched employee rows. Since employees is the left table here and we need all of its rows preserved, the answer is E, which is left join. In this question, we have round robin quantum, which is equal to 4 milliseconds. P1 with 5 milliseconds, P2 with 6 milliseconds, and P3 with 3 milliseconds burst time all arrive together. What would be the completion order using the round robin? So here the correct answer is C, which is P3, P1 and then P2. Let's trace this round by round with a 4 millisecond quantum. Round 1, P1 runs for 4 milliseconds, leaving 1 milliseconds remaining. P2 runs for 4 milliseconds, leaving 2 milliseconds remaining. P3 only needs 3 milliseconds total. So it runs for its full 3 milliseconds and finishes completely with this round. So P3 is done first. In round 2, back to P1, which only had 1 millisecond left, so it runs that 1 millisecond and finishes. So P1 is done second. Then P2, which has 2 milliseconds left, runs that remaining 2 milliseconds and finishes, and that's why P2 is done last. So the completion order would be P3, then P1 and then P2, and hence the answer is option C. Now in this next question, why are B plus trees generally preferred over standard B trees for implementing disk-based database indexes? So the correct answer here is option B. B plus trees store all actual data only in leaf nodes, which are linked sequentially, enabling efficient range queries. This comes down to one core structural difference. In a B plus tree, internal nodes hold only routing keys to guide the search. They don't store actual data at all. Every real record lives in the leaf node, and those leaf nodes are linked together sequentially in a chain. That sequential linkage is what makes range queries like find everything between X and Y so efficient. You simply walk along the leaf chain once you've found the starting point. A standard B tree, by contrast, can have data scattered across internal nodes too, which make that kind of order range traversal far less efficient. Hence, the answer here is option B. In this question, in Java, if a finally block contains a return statement, what happens to any return value or exception that was already pending from the corresponding try or catch block? So the correct answer here is option A. The finally block's return statement overrides and discards the pending return value or exception from try catch. This is a subtle but important Java behavior that's worth remembering precisely. A return statement inside a finally block always wins. It doesn't matter whether the try block already had a return value ready to go or even whether an exception was actively propagating. the finally blocks return statement takes over completely, and that pending return value or exception is simply discarded. Hence, the answer here is option A. In this question, it is asking what is bool of an empty list in Python. The answer here is option A, which is false. This tests Python's truthiness rules for built-in containers. An empty list carries no element, and Python treats all empty containers, whether it is empty lists, empty strings, empty dictionaries, or empty tuples, as falsy values. So calling bool on an empty list, bool of empty brackets, evaluates to false. There is no error raised at all. It's a perfectly normal, well-defined Boolean conversion. The answer here is A, which is false. Next, we have which statement correctly distinguishes paging from segmentation in operating system memory management. The correct answer here is option E. Paging can cause internal fragmentation, while segmentation can cause external fragmentation. This is really about matching each fragmentation type to its cause. Paging splits memory into fixed size frames or pages, and since a process's actual memory need rarely divides evenly into that fixed size, the last allocated page often has leftover wasted space inside it. That's internal fragmentation. Segmentation, on the other hand, divides memory according to logical program units of varying sizes. So the code, stack, data, etc. are having their own spaces. And as these variable size segments get allocated and freed over time, they leave scattered gaps between them that are too small to be reused. That's external fragmentation. So the statement that correctly distinguishes the two is option E, which is paging can cause internal fragmentation while segmentation can cause external fragmentation. Next, we have processes P1, P2, P3 and P4 arrive at the same time with burst times of 6, 8, 7 and 3 milliseconds respectively. Using non-preemptive shortest job first scheduling, what is the average waiting time across all four processes? Here, the correct answer is 7 milliseconds, which is option A. Since all four processes arrive together, SJF simply orders them shortest burst first. That's P4 with 3 milliseconds, then P1 with 6 milliseconds, then P3 with 7 milliseconds, and P2 with 8 milliseconds. Now trace the waiting time for each. P4 runs immediately, so it waits 0 milliseconds. P1 waits for P4 to finish, so it waits 3 milliseconds. P3 waits for both P4 and P1, which is 3 plus 6 or 9 milliseconds. P2 waits for P4, P1 and P3, which is 9 plus 7 or 16 milliseconds. Adding these up, which is 0 plus 3 plus 9 plus 16 equals 28. And dividing by 4 processes gives an average waiting time of 7 milliseconds. In this question, we have a binary semaphore initialized to 1 protects a critical section. What problem arises if a single process performs 2 consecutive wait P operations before any corresponding signal we call immediately before entering the critical section? Here, the correct answer is the process deadlocks itself, which is option B. Let's trace the semaphore value through both wait calls from the same process. It starts at 1. The first wait call decrements it to 0 and the process is allowed to proceed. Then immediately the same process calls wait a second time, but the semaphore is now 0, so the second call blocks the process, forcing it to wait for a signal call. But here's the catch. The only process that could ever call signal to release that semaphore is this very same process, and it's now blocked, unable to execute anything, including that signal call. So it ends up waiting forever for a release that can never come from itself. That self-induced circular wait is a deadlock. Hence, the answer here is option B. Next, we have what is the worst case time complexity of building a min heap from an unsorted array of n elements using the standard bottom-up heapify approach. So the correct answer to this question is option C, which is big O of n. This one often surprises people at first glance. Yes, each individual call to heapify does cost up to of the order log n in the worst case. But here's the key insight. Most of the nodes in a heap sit near the bottom, close to the leaves where heapify barely has any work to do. A leaf node needs 0 swaps. Only a small handful of nodes near the root require the full big O of log n worth of work. When you sum up the actual work done across every level of the heap, rather than just multiplying the worst case by the number of nodes, that sum converges to big O of n and not big O of n log n. This tighter amortized analysis is a classic and frequently tested result. So here the answer is C, which is big O of n. An in-order traversal of a binary search tree produces which of the following results? So here the correct answer is option D, a sequence of node values sorted in ascending order. In-order traversal follows a specific order. Visit the left subtree first, then the current node, then the right subtree. Now recall the defining property of a BST. Every node's left descendants are smaller than it, and every node's right descendants are larger. Combine that property with the left node right traversal pattern, and you naturally end up visiting every value from the smallest to largest, a fully sorted ascending sequence. That's a very elegant and frequently tested property of BSTs. So the answer here is option D. In the next question, we have which of the following sorting algorithms is not stable in its standard typical implementation? Here, the correct answer is option E, which is quicksort. Stability means that two equal elements keep their original relative order after sorting. Standard quicksort's in-place partitioning works by swapping elements around a pivot based on comparisons, and those swaps can end up reordering two equal elements relative to each other, which breaks stability. Merge sort, bubble sort, insertion sort, and counting sort are all stable in their typical standard implementations, since none of them perform swaps that disturb the relative order of equal elements. So the one that is not stable here is option E, which is quicksort. In this next question, we have which data structure is most appropriate for directly evaluating a postfix or a reverse Polish notation arithmetic expression. Here, the correct answer is A, which is stack. So think about the mechanics of postfix evaluation. You scan the expression left to right, pushing each operand as you encounter it. Then whenever you hit an operator, you pop the required number of operands right back off, apply the operation and push the result back on, ready for the next step. That push and pop pattern, where the most recently added item is the first one used, is exactly last in first out behavior, which is the defining characteristic of a stack. That's why a stack is the natural standard structure for this task, and hence the answer is option A, which is stack. Now in this next question, to find the shortest path in terms of number of edges between two nodes in an unweighted, undirected graph, which traversal algorithm should be used? The correct answer here is option B, which is BFS or breadth first search. BFS explores a graph level by level, moving outward from the source node one edge distance at a time. Because of that level by level expansion, the very first time BFS reaches any given node is guaranteed to have arrived via the shortest possible path in terms of number of edges. DFS, by contrast, dives deep down one path before backtracking. So while it can find a path, it offers no such shortest path guarantee. Topological sort and Kruskal's algorithm aren't even applicable here. They solve entirely different problems. So for shortest path in an unweighted graph, the answer is option B, which is breadth first search. Let us look at the next question. In an object-oriented language, when a base class reference or pointer is used to invoke an overridden method and the specific method actually executed, it's determined at runtime based on the object's real derived type, this behavior is known as what? Here, the answer is option C, which is runtime or dynamic polymorphism. The key phrase here is determined at runtime based on the object's real type. That's the defining signature of dynamic or runtime polymorphism. It's typically achieved through virtual functions in C++ or straightforward method overriding in Java, where the call is resolved not by what type the reference is declared as, but by what the object actually is underneath at the moment the program runs. This is different from overloading and static polymorphism, both of which get resolved much earlier at compile time based purely on the declared types. So the answer here is C, runtime or dynamic polymorphism. Next, you have what is the output of the following Python code, where you have x as a list of integers 1, 2, 3, y is equal to x, and we are appending 4 to y and printing x. So you have to say what would be the output of this code. In this question, the right answer is option D, which is a list of integers 1, 2, 3, 4. This tests the very fundamental Python concept, how assignment actually works for mutable objects like lists. The line y equal to x does not create a new independent copy of the list. It simply makes y point to the exact same list object in memory that x already points to. So when we call y.append4, we are modifying that one shared list object, and since x is pointing at that same object, printing x shows the change too. Hence the result is 1, 2, 3, 4 as a list, and the answer is D. In this next question, we have a 2 GHz CPU averages 5 cycles per instruction. You will have to calculate the ideal instruction throughput, which would be in approximately how many MIPS. The correct answer here is option C, which is 400 MIPS. Let's convert this step by step. A 2 GHz clock speed means 2000 million cycles happen every second. If each instruction takes an average of 5 cycles to complete, we divide the total cycles per second by the cycles needed per instruction. So 2000 million divided by 5 gives us 400 million instructions per second. In other words, 400 MIPS. Hence the answer is C, 400 MIPS. And that brings us to the end of mock test 3 of our IBPS SO IT preliminary exam series. If this session helped you, do like, share and subscribe so that you don't miss mock test 4. Keep practicing, stay consistent, and I'll see you in the next session. Thank you for watching.